Now, our next speaker is a principal scientist, acting deputy executive director, research, and head of the communications and networks department at the Institute of Infocomm Research. She is editor-in-chief of IEEE Open Journal of Vehicular Technology, a distinguished speaker of the IEEE Vehicular Technology Society, a member at large with the IEEE Communications Society, and a member of the IEEE Vehicular Technology Society Board of Governors. She's also the chairperson of the Special 5G Strategy Task Force, Telecommunication Standards Advisory Committee, or TSAC, sometimes pronounced as TSAC, of Infocomm Media Development Authority, or IMDA, Singapore. And she's also the chairperson of TSAC's Future Networks Work Group, leading the TSAC's standard development activities in future networks. Ladies and gentlemen, please welcome Professor Sun Sumei.
Thank you, Mr. Chair, for your very nice introduction. A very good day to all of you who are dialing in to attend this workshop. I'm very honored to have this opportunity to share with you some of our understanding in the related aspects when we move from 5G to 6G. To start with, let's first take a look at the megatrends when we move to 2030, which have been given by a few survey reports coming from DNL, Frost and Sullivan, and also the MIT Sloan Management Review. When we look at all these different megatrends predictions, we can see a converged theme, including hyperconnectivity, artificial intelligence of everything. And certainly, we are also seeing some of the even more eye-catching keywords. For example, connected living, Industry 5.0, every device is connected, zero latency world, and so on. So with this, we can also easily relate that the new trending words of metaverse is one integrated part of these megatrends when we move to 2030. So with this megatrend in mind, let's now take a look at the cellular evolution. When we move from first generation of 1G to the fifth generation of 5G, we have shown here the services that have been enabled when we evolve in our 40 years of journey from 1G to 5G. We have also shown a few interesting terminals or handphones that we evolve during this cellular evolution. So at the same time, we can also see the services we have enabled in terms of the data rates, the network capacity or capability we can offer from 1G to 5G. And when we move today into 5G network, we can see that from the very humble only voice communications in 1G, we are able to provide tens of gigabits per second of data rate with milliseconds level of latency. And of course, this is to enable the services, for example, vehicular communications, Internet of Things, and so on. If we look at the evolution map further, we can also notice a very interesting trend as we summarize here. From 1G to 4G, the technology evolution have all been focused on human services with the people as our centric user. And in terms of the performance of the network, we have been focusing on the data rate. And when we move from 4G to 5G, we have added to the people-centric services to also people and things-centric services. And of course, for the network performance, we have added on top of the data rate and capacity, also the latency. And of course, with this, we are able to enable many services. Now, the question is, given the megatrends to 2030, how would the evolution to 6G that is going to drive our research? Looking at also some of the published white papers in 6G, we can also see some converging trend that is very well aligned with the mega trend we have shared just now. That is actually summarized into these 3 walls of convergence. The 3 walls will be physical world, virtual world, and also the human world. And of course, with that, we are also looking at one more performance indicator in the 6G network design on top of the data rate and latency. That is the network synchronization. Because when we have to converge these 3 walls, the human, the virtual, and also the physical, we will need to make also these 3 walls synchronized together with very high precision, with very high accuracy. So sharing this vision, now it is time to also take a look at the reality for the 5G vision. 5G, as we have just reviewed, is innovation to connect people and things, with which it is able to enable the digital transformation of all the industry verticals. Indeed, it is very well illustrated by this published 5G vision by GSMA, I think more than 10 years ago. So 2 or 3 years into the 5G deployment over the world, how are we doing now? With all these, very demanding KPIs for 5G, including the high reliability, low latency, high density connection, and so on. And it is interesting and important to also mention here that most of these KPIs for 5G have been defined to focus on the individual sections and also individual applications. Whereas when we enable these 5G services for digital transformation, in many of the use cases, we will need to have all these KPIs to be guaranteed simultaneously, and very often to be enabled in a dense local area, which may not be so friendly for deploying the wireless services, as we are going to see in the next few slides. So to address the problem that we want to make, I'd like to share the Singapore's 5G lead verticals and also use cases for 5G, summarized in this slide. Of course, being a harbor city, maritime application for 5G will lead the league. Urban mobility, Industry 4.0, smart estate, and also, of course, also top the list of the verticals and also use cases. So what are the use cases that we are driving in the different verticals? These are given with these little small illustrations here. And again, if you look at the converging use cases in the various sectors, in the various verticals, we also see some convergence leading to autonomous vehicles, either moving on the ground or flying in the air, which are actually indicated as AGVs, drones, and also the autonomous vehicles moving on the road, carrying passengers and so on. And of course, in these different verticals, we also see some of the leading IoT applications, for example, with the predictive maintenance, smart traffic monitoring, energy management, and so on. These are the typical examples for 5G to enable the connectivity for things, as we have shared just now. And of course, to support even more intelligent digital transformation, we have also the augmented reality, virtual reality, teleoperation, supported by robotic and automation, artificial intelligence, and so on. So indeed, these are really very attractive applications and use cases, and at the same time demanding and challenging. Why challenging? Let me share with you this example in maritime. Singapore has started the 5G trial and the use case experiments very early in 2019 for the maritime sector of transformation. And included in this slide is actually the future possibilities that can be enabled by 5G as driven by the Maritime and Port Authority, or MPA of Singapore, and also the Infocomm Media Development Authority of Singapore. And shown here in the theme by these 9 and 10 examples, in fact, we can see that really the demanding services for 5G in the maritime is massive connectivity at the port and also at the sea with the high data rate support, high capacity support, and also the ultra reliability and low latency communications capabilities. At the same time, the high precision localization, which really are going to transform the future of ports in Singapore. However, if we look at the application environment, we are powered with containers at the port and also many ships docked at the sea near the shore. And we are envisioned to have many of these AGVs are manned, coordinated and managed by the communication links with very high precision localization, and also unmanned operations by drones and other robots to enable the digital services. Containers and ships will suggest a lot of metallic structures, which will block the wireless signals. And at the same time, the blocking will have to be overcome so as to enable all these services. So we have the open problems and challenges to address, as summarized in the bottom of this slide. That is to guarantee all the demanding quality of service to meet the KPIs in the local area of the port and also the near port sea areas. And the busy port operations also suggest that we have a very dynamically changing and also wireless hostile environment, hostile channels for us to deliver the wireless services. And at the same time, automatic and unmanned piloting of these ships would also request us for this highly integrated terrestrial and non-terrestrial communications, including the sky, air, ground, and also sea, for seamless transition and real-time services. Indeed, this presents, if not the most, but one of the most challenging scenarios to deploy 5G services. Another example I'd like to share is 5G in smart urban solutions, or in particular smart construction, that we are working closely with the Singapore's Housing Development Board in Singapore. So what smart services are we enabling in the smart construction by 5G? Is illustrated by this primitive drawing, but I think it will give the ideas clearly. As you can see that we have drones operating on top of the construction site, and also we have different robots moving around at the construction site. So what do we do with all these drones and also the robots? For the drones, which are embedded with LiDAR and also cameras, we like to deploy them so as to enable the automatic and real-time facade inspection, safety event detection, so that we are able to reduce the manpower requirement and also to have more real-time situation awareness. And for the robots, which are able to navigate much more easily with these legged or rolled robots, we are able to build a real-time digital twin system to monitor and also manage the construction operations. So looking at these two use cases for smart construction, we can see that we will need to enable URLLC, high resolution and real-time video, and also the remote real-time operation enabled by the digital twin. And of course, at the same time, for the construction site, we are also having a not very friendly deployment scenario for wireless because of the blocking, because of the dynamic changing environment, the dynamic changing wireless channels due to the many construction activities. So one more example I'd like to share is really the end-to-end connectivity, end-to-end track and trace in the advanced manufacturing. So we have shown quite a few examples of use cases for the smart manufacturing by 5G. And of course, this is only focused on the manufacturing floor in a localized area. However, smart manufacturing is not only just about a localized areas of service, but end-to-end from the supply chain, as illustrated here, in the supply management, in the warehouse management, inventory management, very well, and also real-time integrated with the manufacturing floor. And for some of the hyper-personalized products development and also services, we may need to also have the real-time awareness to the end users, to the end customers. So with this, again, the services will demand for high data rate, for high capacity, and also URLLC to be served both in the localized area, but also end-to-end. And certainly this presents also a converged open challenge, open problem for us to address. That is again the QoS guarantee of all these demanding KPIs in the local area as well as the wide area. And we have to deal with these challenges with the wireless hostile channels and the dynamically changing channels as well. So shown here is a little bit different problem as what we are doing in 5G for smart grid or in energy grid. When we drive the sustainability roadmap, we need to engage and enable more and more of the renewable energy integration into the smart grid. And of course, we want to manage the renewable energies and integrate them seamlessly with real-time mobility, with real-time monitoring and also real-time management. And for that, we will have to enable the two-way URLLC communications between the management platform as termed as the virtual power plant and also the renewable energy assets deployed in a wide geographical areas. And for those wide geographical areas of deployment of the renewable energy facilities, we will need to enable the high reliability, low latency services, and also importantly, the high availability and resilient connectivity. And of course, for this critical industry infrastructure in operation, we will need to guarantee security in design and also enable the data auditability in the communication networks too. So one interesting challenge for this problem will be, of course, on top of the URLC and the short packet nature of transmission, is the coexistence with the public service. Public service means the other industrial use cases and also the consumer use cases that needs to coexist in the public operator managed networks. So will the network slicing be able to address this challenge? We are actually working on this project in collaboration with the Energy Management Authority of Singapore and also a few industry collaborators and the Energy Research Institute in NTU to address this problem and enable the wireless services for the virtual power plant. So with this, I think we have shared the 6G vision and also the 5G vision. And we have done the reality check on the current 5G deployment and some of the gaps we may need to bridge for 5G in the various digital transformation vertical applications. And so that is actually pointing to the 5G to 6G evolution as summarized by this title of the slide. That is, 6G will need to further push the curve so as to be able to address the problems that we have shared and then enable the vision of the three worlds of convergence for physical, virtual, and the human worlds. And indeed, this common vision has been already, advocated by the many sharings of white papers and also the presentations. And given here are just 3 examples which are indicating the vision of 6G in China by this research paper, and also the presentation by Professor Dabao when he was with Huawei, and also the published white paper by Samsung. And of course, there are many other ongoing efforts worldwide to actually to share the 6G vision, to also move the 6G research activities. But I'd like to pause here and also spend a little bit time explaining using the center illustration on the further aspects of the 6G. Of course, we always have, if you recall, the data rate, the latency. And we have also briefly shared that for 6G to achieve these three walls of the convergence, we will need to have also the network synchronization. Only then are we able to have the aligned and real-time synchronized three walls of convergence. And of course, that network synchronization will be indicated by this performance indicator. The first is related to the network synchronization accuracy in terms of the jitter, and also the synchronization accuracy will be moved to 0.1 milliseconds. But the jitter of the synchronization, that means the changes in terms of the synchronization alignment will have to be within the 10 nanoseconds level. And that gave us actually a new design challenge in 6G. So only then maybe we are able to serve more capacities and also address the challenges we have mentioned, either partly or fully. So with this, let's take a look at what are the technologies to drive to support this 5G to 6G vision. So we summarize the evolution with these few aspects. The first aspect will be represented by serving machine as the dominant user in 6G networks. And of course, for serving machine as the dominant user, we will have to further evolve the technologies to achieve agile multiple access and support packing more users into the network. And we have already shared that we will need to achieve high precision wireless synchronization represented by this wireless time sensitive network design. And of course, for machines as a dominant user, we will need to further integrate the sensing capability with communication, computing, and also control design. As one representative technology to drive this evolution, radar communication co-design will be one commonly identified technology for 6G. And of course, when we pack more users into the network, the machine users into the network, the network architecture and also antenna technologies will need to further evolve so as to support the performance demands of these machine users. Another dominant factor to support this 5G to 6G evolution, we believe, will be represented by this agile SDX or software-defined everything as a necessity. And SDX will move from the software-defined radio network to also the software-defined environment. And one representative technology, as shared by yesterday's keynote, will be this large intelligent surface technologies. How are we going to embed the large intelligent surface into the environment, make it immersive, and at the same time serve the network and the communication requirements? And of course, as a classical topic, when we move from one generation to another, we always are going to get or request for more spectrum so as to support the more demanding services and more services. And of course, coming to research will be always this challenge of managing this heterogeneous spectrum access, it with agility and also with intelligence, and moving into the next generation. Open network will continue as a driving R&D topic, we believe. And of course, when we enable the various digital transformation for both human users and also for machines, we will need to also make it into the design for privacy guarantee, for security protection, and also make the network resilient so that we are able to support those critical industry operations. So for that, we need to look at how are we going to embed the privacy and security resilience requirement into the design. How are we going to look at and relook at the communications, security, and also the computing co-design. And of course, for the machine users, the security protocol design may need to also be looked into as the machine to respond to, for example, the multi-factor authentication will have to be re-looked into as well. And certainly, quantum security will be a critical aspect of 6G security. Last but not least, sustainability, sustainable networking, and also energy efficiency will have to be the baseline for all these design features in 6G. And the driver or the engine for all this design will be this artificial intelligence. To embed artificial intelligence, to make use of artificial intelligence to push for the optimization of the design and also to push for the optimization of the management of the 6G systems and also networks. So moving quickly, I'm going to share a few design examples that we are working at I2R, including the radar communications co-design, heterogeneous spectrum access, and also some AI aspects in networking. So first, please allow me to share our work in the joint radar communications design as an example of the integrated sensing and communication systems. The goal and motivation for the joint radar communications really is to realize this vision of using one single system in a shared spectrum to support multiple functions of sensing and communications. As a motivating example, we are sharing actually the transportation use case. We can see that we are having vehicular users and also pedestrians moving along the roadside. And traditionally, we will have V2V communications either by the IEEE DSRC or the cellular V2X in 4G and 5G, as represented by the blue arrows. And at the same time, to manage the safety, especially when we have more and more of this assisted driving and also autonomous driving, we have the vehicular radar embedded on the vehicles so that we are able to avoid collision and improve the road safety. And the radar signal transmission are represented by the red dashed lines. Traditionally, they are designed into separate systems using different spectrum, using different waveforms. But now, with the more and more applications of wireless, including radar and also communications, we actually may now have the luxury of having separate spectrums for radar and also for comms. So are we able to realize this vision of using one single system in the shared spectrum but support both functions? In fact, if we look at this block diagram illustration, these two systems of radar and comms does share many common blocks, such as amplifiers, up conversion, down conversion, the analog and digital conversion, and also the baseband processing units share some common modules as well. And of course, radar is for detection, and then comms is for the information transmission. So indeed, with these binary common design blocks, it seems feasible to have this joint radar comms possible, right? And of course, to design the joint radar communications, there are going to be multiple options. For example, the first option, of course, is to make use of the communication waveforms to enable radar sensing functions. And the second option is to embed communication signals in the radar waveform so that we are able to share information when we run the radar sensing. The third option will be to have, dedicated radar communication waveforms, but we timeshare these two functionalities. And certainly, there are going to be both pros and cons for the various options. What are the performance requirements for the two functionalities? In fact, they represent different requirements. And for communications, we have URLC for safety critical information and high data rate for other applications. For example, transfer videos and so on. And for radar sensing, we will need to fulfill the requirement of high resolution, simultaneous multi-target detection, and also high accuracy in terms of the localization and also speed detection. And indicated here are examples in the vehicular applications, which request for sub-meter level of localization accuracy and also sub-meter per second of speed detection accuracy. And of course, for both systems, we will need to design them to be secure in terms of anti-jamming capabilities, anti-spoofing capabilities. So with that, are we able to achieve it? Indeed, as shown by our evaluation using practical waveforms. And indicated here is actually the single carrier frequency domain equalization based 11AD Wi-Fi waveform in the 60 gigahertz band. We make use of the 11AD waveform to transfer information signals and at the same time using the reflected signals to run the localization or rendering detection and the speed detection. As you can see from these plots, indicating here in the black curve, the speed detection accuracy versus the ISNR range and also the rendering accuracy in terms of the localization error. We can see we are able to satisfy the requirement of sub-meter per second of speed detection accuracy and also the centimeter level of rendering accuracy on top of the gigabits per second of communication performance. So having proved that this concept is feasible, we are now moving to realize this system into a hardware prototype. And certainly, we are keen also to look at enabling this in the 5G systems using the standard 5G compliant waveform. And of course, some further challenges will need to be addressed as well, including the self-interference mitigation in the full duplex operation for the joint radar comms system, and also the multi-radar comms interference mitigation mechanisms too. And when we move from 5G to 6G, another interesting research aspect is optimized waveform to support this dual function instead of using one waveform for dual function, but always optimized for only one single function. So certainly when we move from 5G to 6G, in addition to this new possibility of optimized joint radar comms waveform design, there is also other aspects. For example, beamforming design. For the multi-antenna arrays, anti-jamming, anti-spoofing will remain as another challenge for us to address. And one more important aspect is to support the dual function. What protocol aspects do we need to embed in the 6G design so that we are able to support seamlessly the multi-functions and also the multi-function to single function transition? Next, I'm going to share very briefly the next problem, which is always with us. That is in terms of the spectrum access, dynamic spectrum management, and also agile software-defined spectrum aggregation. And you can see from this busy chart and also illustration that there is really not much spectrum resources for us to tap on when we move from 5G to 6G, but only those little small holes in the lower spectrum and more in the higher spectrum when we move, for example, from millimeter wave to the sub-terahertz band. And of course, with all this, we are present with even more challenges. From the spectrum scarcity, then it comes to the spectrum availability. And of course, how are we going to access and also aggregate all these heterogeneous spectrums in the different part of the spectrum? And also with this aggregation requirement, how do we handle the system design complexity so that we are able to indeed support the keyword of agility when we aggregate the spectrums? So what we are doing in I2R is to realize this agile spectrum aggregation by enabling the software-defined nature. To do this, we are moving away from the conventional filter bank approach to a single wideband converter as given in this illustration. So at the left-hand side of this slide, we are seeing the conventional structure that when we operate multiple bands, we will have to enable multiple filters so that we are able to support the operations in the different bands. And of course, different filters will correspond to also different local oscillators. And of course, with this, we will have the challenges of high hardware complexity and also lack of flexibility or agility. And also different bands may have different impairment models for us to handle as well. So if we are able to move from this filter bank architecture to a single wideband converter, that we will aggregate these spectrums over the air, but convert them using one single wideband converter, and then we are able to have a much more lean hardware architecture at the receiving end. And of course, if we are able to configure this converter using software-defined design features, we will be able to even reconfigure the different subbands flexibly. So is this possible? Indeed, I think with all these described advantages, I'd like to share with you quickly that this is not really just on paper with mathematical derivations, but possible, even proven with our hardware. And you can see that we are showing here of aggregating two spectrums in two different bands. And in both bands, we are transferring the 5G waveform modulated with 64 QAM signals. And this is the received and detected waveform. And you can see that they are very clean, representing very good signal integrity and also good EVM characteristics. So of course, moving further, this part of the research, we would like to see the possibility of aggregating even more bands and also to push for even higher performance so that we are able to support higher order modulations, wider bandwidth of aggregation, and so on. So we still have a long way to go. Next, I'm going to quickly share the AI aspects as a performance driver in the 6G research. Indeed, there are many active research going on already in enabling AI in communications. And shown here are really, the pervasive AI in all the different layers of the networks, coming from the device level, the radio access network level, at the edge level, and also at the cloud level, so that we are able to also manage the wide area network. And of course, with this, we would like to achieve the architectural support, and also we can move to have a intelligent network operation tool. And if we go from, of course, to do this, we still need to address the challenges, including interpretability, controllability, and also robustness of the AI design. And certainly, we will need the standardization to embrace incorporating AI in the protocol layers too. So, excuse me, if we look at the incorporation of AI in the various communication layers in the OSI model, there are indeed many open problems for us to work on, ranging from the circuit level to mitigate the impairments in the circuits, to the physical layer, all the way to the network operations. In the interest of time, I'm not going to share a lot of details, but rather I'm going to run a few quick examples. And the first example I'm showing here is to embed the machine learning and deep learning models to address the circuit impairment. And shown in this example here is to use deep learning neural network architecture to linearize the power amplifier, which is a classical design problem in our high power amplifiers. And indeed, our results shown very encouraging performance as indicated here in terms of the power spectral density behavior after including the deep neural network. And that is indicated by this lowest curve, of course. We would like to show the best performance, lowest curve in terms of the sideband leakage, but the highest in terms of the band of interest. And this is not just achievable from the simulation, but also actually achieved using this test bench with a real hardware setup too. And the next example is actually machine learning in link adaptation, so that we are able to learn much better and more accurately about the channel characteristics, so that we are able to drive a much more accurate link adaptation performance. And of course, the benefit will be giving us higher capacity in the network, and also for each individual users, we are able to run for even better quality of service, quality of experience delivery. And certainly, using deep learning for detecting anomalies in the network operations is a hot research topic too. And we have also done some related work, and it is still ongoing as well, of course. And the key focus here is really how the possibility of using a low number of data samples to achieve efficient training and also high accuracy detection. And the results shows that this is possible. Of course, we have also learned a lot from our machine learning and deep learning colleagues in the institute, so that we are able to develop efficient machine learning models. So with this, of course, driving performance of using AI in 6G, there is also another ongoing active discussions, that is actually semantic communications, which might be a paradigm shift. But the question is, with this paradigm shift, how are we going to also drive the standardization effort so that we are able to embrace the benefit of semantic communications when we have sufficient validation? So it may be a food for thought when we come back from this discussion. So quickly, I'd like to address the last topic in my presentation, that is in the 6G standardization. First, let's take a look at the organizations involved in the standardization efforts. And in fact, for any standardization development in communications and networks, we will involve 3 organizations, namely the standard development organizations, or SDOs, which are responsible to develop the technical specifications, and then the regulatory bodies and also the administrators who are responsible for the regulatory and also the legal requirements. And then also the next one is the industry forums, which are driving the specific technologies or interests. And now let's take a look at the detailed level of information. First, we start with the SDO. And then again, for SDO, we can look at, we can see that we have different levels of SDOs, ranging from global SDOs, regionals, and also nationals. As a very good representation, 3GPP, who is behind the standards of 3G, 4G, 5G, is actually the global SDO. Regional SDO, one good example is the European Telecommunication Standard Institute. It's a European SDO. And for national SDOs, we have like those representations given in Japan, US, and so on. And of course, in Singapore, it is IMDA. And we have also, excuse me, I shouldn't mention that. I think IMDA should be under the regulatory organization. So what are the responsibilities for the regulatory bodies and administrations? Remember the busy chart of the spectrum, right? So one key responsibility among all is actually regulate the spectrums, so that all the different geographical locations and also the different organizations will agree to the common spectrum regulation, so that we are able to enjoy roaming, for example. And of course, another aspect is on the regulatory certification type approval for the devices and equipments. And as a example, we can see for spectrum regulation, it is managed by ITU, the International Telecommunication Union. And also we have the regional ones in Europe, in US, Asia, and so on. And of course, from the regional, we will need also penetrate down the coordination into the national level, so that we are able to achieve this aligned spectrum regulation. And then industry forums, as we mentioned, it is usually driving for some specific technologies for certain verticals. in some cases. And shown here are some examples like the GSMA, NGMN is more for the networking aspect of the technologies. NextG Alliance, Aura Alliance are some of the newly established alliances or industry forums. For example, ORAN and ONET will be focusing on open networking in RAN and also in the core network. 6GIA is specific in the industry digital transformation aspects of the technology development. So with that, it's also good time to look at the evolution roadmap from 5G to 6G. As we started this presentation, we have actually up to 2030 to realize our vision and complete this evolution roadmap. And of course, to do that, there are many details and also a lot of hard work involved, as indicated here, from the standard aspect to the regulation aspects, and also, of course, the research and also the technology development. So for that, we are open and also look forward to working with you and look forward to collaborating with you. With that, I will stop here with my presentation. I would like to take this opportunity to thank you again for your attention, and I'm happy to answer any questions if you have. Thank you.
Thank you so much, Professor Sun Sumei, for that very comprehensive presentation. And of course, we'll now quickly move to the Q&A segment. And we have a question from our audience right now, and it's this. For 6G, AI itself is going to be standardized or the protocol only? What do you think, Professor?
Yeah, thank you so much, Wayne, for this very good question. As I mentioned, in fact, for AI to drive the performance, we have actually both the standard enabled aspects as well as the implementation aspects. In fact, there have already been activities in the various standardization bodies to study and also look at how to embed the AI aspects in the next generation of the standardized standards. And of course, on top of that, as I illustrated in my presentation, we have also the implementation aspects, for example, the network management and also the business aspect of AI in the network services. Those may require less standardization, but more for the machine learning and AI model to further push the performance curve.
Thank you so much, Prof. We've got 3 more minutes. Maybe we'll handle one more question over here. And
Sure.
It's this one. You have shared a design example on the software-defined carrier aggregation. Can you share some of the remaining related research challenges?
Sure. Yes, I will be happy. And in fact, if you allow me, I will continue endlessly, because there are indeed, a lot of challenges, because we do not face a static problem statement even. Let me share more on this aspect. We know that in 5G, for Singapore, we have been given 2 regulated bands, right? One is the low band in the 3.5 gigahertz part of the spectrum. And then the other one is in the millimeter wave bands, which is in the 26 gigahertz range. And at the same time, we have also the unlicensed spectrum, which includes the 2.4 gigahertz and the 5 gigahertz, which have been taken up by, for example, Wi-Fi, Bluetooth, Zigbee, and so on. So it's certainly, this has already given us a very good indicator that to enable this single converter kind of aggregation with agility, we have to handle such a wide range from as low as 2.4 to as high as 28 gigahertz. And then when we move ahead, we know that we have already been looking at refarming some of the spectrums from the legacy systems, and in particular in 3G. And that gave us some of the new spectrum to add into the play. And in our Singapore case, it is the 2.1 gigahertz band. And when we move from 5G to 6G, we have already many activities looking into the terahertz band of the transceiver design. So this will give us actually the design challenge of, not only the system optimization, but also the semiconductor design, the IC design requirements too. So it is not really just a communication engineer or communication researcher's problem, but also, we will need to work together with our circuit IC design colleagues to work on the problem together. So yeah, there is a lot of interesting problems, and also that will drive us actually to continue working on this.
Thank you so much, Professor Sun. Of course, I wish we could continue to chat more, but we are just out of time. And just want to thank you so much for that detailed discussion on 5G to 6G driving applications, enabling technologies, research, and standardization. Thank you so much, Professor.
Thank you.